So, thank you for the introduction. Yeah, I'm going to talk a bit about in situ precipitation, or the possibility of in situ precipitation hardening in lightweight high manganese steels. Maybe you've already seen the talk of Jan yesterday. He also talked about the steel, but he was more on the processing side. I'm going to go into more detail of the material. Okay, so first I'm going to talk about why we want to print this lightweight high manganese steel, what type of alloy lightweight high manganese steels are, and why we are trying to process it in additive manufacturing, or specifically DED. And then I'm going to show you a couple of microstructures and mechanical properties for the alloy. And finally, at the end, some key takeaways. So what are lightweight high manganese steels? We are looking at this kind of alloy. So it has 1.1% carbon, 30 weight% manganese, and 8 weight% aluminium. It's a fully austenitic alloy with the possibility to precipitate nanoscale coherent copper carbides in the matrix. And if we take a look at some cathode calculation, you can see here that it's fully austenitic above about 800 degrees C, and between 500 and let's say 750 degrees C, you have the possibility to precipitate this coherent copper carbide phase. As you can also see, the volume fraction is quite high, so up to 20%. And that's also usually the point where you do the heat treatment of conventionally produced lightweight high manganese steels. In the microstructure, it kind of looks like this. This is an ECCI image. You can see this kind of basket weave microstructure in here, and these are very fine cuboid copper carbides with a size of about 10 to 20 nanometers. And you can also see that most of the time some kind of grain boundary phase is forming. This is also copper carbide, but it's incoherent copper carbide phase. And this leads to a couple of problems in additive manufacturing we're going to get later to. Another advantage of this alloy is that dislocation glide is confined to planar glide, which leads to the effect called shear band refinement-induced plasticity. It kind of works like twinning-induced plasticity, where you get dynamic Hall patch hardening during deformation. This approach to alloy design is very beneficial, as you can see here in this SQ plot with ultimate tensile strength and total elongation. You can see that these S-strip high manganese steels are in the second generation of advanced high strength steel and have a very high strength and ductility combination. And additionally, as I showed you on the last slide, it has like 8 weight% aluminium, which means that the density is reduced compared to other steels. However, this alloy is not really applied in industrial application because you need energy-intensive post-processing, mainly to the strong segregation of manganese during casting, stuff like that. So, why are we going to try to print that by AM? It's first to reduce the processing steps necessary to get parts out of the steel. Furthermore, we want to use the processing heat in the AM process to precipitate these copper carbides, again shortening the processing steps necessary. And we could already show, like a lot of years ago, I think it was about 5 years ago, that it's comparatively easy to manufacture high manganese steels by DED. Okay, so what types of methods are we using? We are using a DED process with different preheating temperatures. Again, if you're more interested in the processing side of things, maybe ask Jan, or maybe you already know that if you attended this talk yesterday. And we monitored the temperature by a thermocouple. We also applied this material to PBF with no and 550 degrees C preheating. We were able to manufacture fully dense samples, about I don't know, 99.5% was pretty easily reached. And again, one problem was that we had strong strain edge cracking, which, I mean, just to quickly show that, this is a fracture surface of a printed sample after tensile testing. And there you can see a very smooth grain boundary. And on this grain boundary, you see these precipitates here. And this is the incoherent copper carbide phase, which forms during the process, and thermal stresses finally lead to grain boundary cracking and very not reproducible mechanical properties, at least in tensile testing. But let's focus more on the in situ precipitation hardening aspect. So let's take a look at the microstructure. So here's a light optic micrograph. You can see it just looks like a DED microstructure. And if we take some EDS measurements, you can see that we have quite strong segregation of manganese in this alloy, and it also leads to carbon segregation. And this also changes the stability of the copper carbides. So I brought you two CAFAT calculations, one for the dendrite core, so the manganese pore region, where you can see that copper carbides are a lot less stable and also are only precipitated to about, let's say, 650 degrees C. Whereas in the interdendritic region, you can see the higher manganese content leads to a higher stability of the copper carbide phase, which can be precipitated to, let's say, 800 degrees C, and even with a high volume fraction. So let's take a closer look at the microstructure. So first we're going to take a look at the microstructure without preheating, and the thermocouple told us that the process is taking place at around 500 degrees C, and that's much too low to precipitate copper carbides during sample manufacturing, just because the kinetics are way too low. And I mean, this is just a normal DED microstructure at this point. But if we increase the preheating temperature to 500 degrees C, our process takes place at around 650 degrees C. And there we can see copper carbide precipitation. So first, a microstructure on top of the sample, which means this position has seen a low amount of heat. And there you can see, like, this is not noise, this is etching of the copper carbide phase in the manganese pore, even in the manganese pore regions, but you see a higher volume fraction in the manganese rich regions. And if you take a look at the microstructure at the bottom of the sample, which has seen much higher amount of heat, you can even see high amounts of copper carbides in the dendrite cores. So the kinetics are high enough to precipitate the copper carbides. And just to confirm that these are really copper carbides, this is a 10 TM measurement with a SAD pattern in 011 zone axis. So the large spots are from the FCC phase. And in between here, like these faint spots are the superlattice reflections of the copper carbide phase. So it was possible to precipitate the copper carbides during the DED processing. And the influence on the mechanical properties are a bit difficult to determine, at least in tensile testing, again, because of strong strain edge cracking. But if we take a look at the hardness, so these are curves at different preheating temperatures, so 0 and 300 degree preheating led to a mean hardness of about 270 Vickers hardness. And in the 500 degrees preheated thing, we see a strong increase in hardness. So it really did lead to a strengthening effect. And even though the properties are very scattered in tensile testing, so here you can see you have a lot of scattering of the elongation. due to strain age cracking, but still what you can see here, so the blue curve is without preheating and the orange curves are with preheating. If you take a look at the strain hardening rate, you can see that the strain hardening is much higher in the samples without preheating than in the samples with preheating. And this is again a result of the formation of copper carbides, because they inhibit the S-strip effect during deformation, and therefore the strain hardening rate goes down. Okay, and another important effect in this alloy is again this S-strip effect. And compared to conventionally produced material, you have a segregated microstructure, and we were also interested to see if the segregated microstructure somehow influences this S-strip behavior. So, and it does not. This is a sample after tensile testing without preheating and 500 degrees C preheating. And all these lines, what you're seeing here, are these shear bands which are formed from the planar glide of the dislocations. And I don't think it's very clear in this image, but a couple of segregated zones are definitely going through this image here, and you cannot really see an interruption in these S-strip formation, which kind of makes sense because the S-strip effect is usually associated with or facilitated by the formation of short-range orders, which is kind of like a pre-stage of the copper carbide. And the copper carbide is stable in both the segregated and not segregated zones. So it does not influence the S-strip mechanism. So what have we learned? In situ precipitation of copper carbides is possible in this alloy during DED processing, where we get increased strength and lower S-strip activity by the formation of copper carbides, just like in conventionally produced material. The precipitation amount is higher in the segregated zones due to higher stability of the copper carbides. However, we have very strong strain age cracking, which prevented reproducible materials properties, which is why, at least in my opinion, this material is definitely not suited for additive manufacturing. But maybe someone has an idea to improve this alloy to increase weldability and maybe make manufacturing possible. So, thank you for your attention.